Hello friends, welcome to engineering tutorial. So today we are going to start a new discussion on different subject which we have covered in the past, but a new concept related to that. So we'll be resuming our discussion on digital electronics, and today we are going to discuss a new method of simplifying or minimizing Boolean expressions. So if you check the playlist related to digital electronics, you will find that so far we have discussed relating to simplification of Boolean expressions, okay, simplifying or simplification of Boolean expressions. We have discussed first the simple straightforward method using Boolean algebra laws, okay, reduction using Boolean algebra laws. Then we have discussed the Carnot map method or the K-map method, where we have discussed the simplification of 3 variable and 4 variable SOP and POS type expressions. Here also SOP and POS type both we have discussed in Boolean algebra laws. So in this method, in this video, we are going to discuss another new method which is called as Quine-McCluskey tabular method or table method. Okay, this is the method which we'll discuss. So why this method? See, Carnot map or K-map, it is a convenient and economical method when it comes to 3 and 4 variable. Okay, 3 and 4 variable Boolean terms or Boolean expressions consisting of 3 and 4 variable, for that K-map method is suitable. But when the number of variables are greater than 4, that is 5 variable, 6 variable, 7 variable, then it becomes very complicated, complex, time consuming to use the K-map, and the possibility of mistakes that also increases. So for that purpose the Quine-McCluskey table method is used. We can also use the K-map method for 5 and 6 variable Boolean expressions. That we'll discuss separate video. I have not covered that, but still it is very lengthy and time consuming, and the chances of making mistakes are very high. So Quine-McCluskey method, it's a very good choice for that. So we will be using this Quine-McCluskey table method. First we'll discuss simple problems using QMT method. We'll call it the QMT method, Quine-McCluskey table method. Okay, so we'll first use this method to solve a few 3 variable questions, then we'll go to 4 variable questions, and then we'll discuss 5 or 6 variable. See, 5 and 6 variable questions, they rarely come in exam. Okay, it's mostly related to 3 and 4 variable, but we should know the basic concepts related to Quine-McCluskey. So why I am starting with 3 variable? Because if I directly go to 5 and 6 variable using Quine-McCluskey, then you will get confused. So we'll start with the basics, the 3 variable. We'll discuss not many questions, 2 or 3 questions we'll discuss. Then we'll discuss the majority number of questions on 4 variable QMT method. That will give us the good understanding about what the QMT method is all about. And then we'll discuss some questions on 5 and 6 variable. Also we'll discuss 5 and 6 variable K-map method also. So we'll cover these things. So we'll discuss the Quine-McCluskey table method or QMT method. Directly we'll be solving questions, and in that I will explain you how to carry on the different steps related to it. Okay, so here we will be solving some simplification questions using QMT method. So here we have this Boolean expression consisting of 3 variables. As I said, we'll be starting with some 3 variable questions, then we'll go to 4 variable and then 5 and 6 variable. Okay. So the Boolean expression is given as f a b c 3 variables, and it is given as minterms 1 3 5 7. We have to simplify it using QMT method. So here a number of steps are there. You should follow each step, carefully, because a large number of steps are there, and if in any particular step you make one mistake, in one particular bit even you make a mistake, then the whole solution will be wrong. Okay, so patiently, carefully, follow each and every step. First, step 1. We have to represent each minterm in terms of their binary equivalents. Okay, this. So we have 1 3 5 7. So first, the minterms and their binary equivalents. Minterm 1, it is 0 0 1. Okay. 3, it is 0 1 1. Okay. 5, it is 1 0 1, and 7, it is 1 1 1. So if you remember the basic concepts related to sum of products, product of sums, min terms, max terms, I've already discussed in detail in the previous videos. So you can check the digital electronics playlist for that. So this is here basically A bar, B bar, C. This is A bar, B, C. This is A, B bar, C, and this is A, B, C. Okay. Just for the sake of clarity here, I have expressed it, I have highlighted it, okay, so that there is no confusion. Okay, we have represented it in terms of their binary equivalents. Next step, step 2, is arranging all the binary equivalents, okay, binary equivalents of minterms, okay, the binary equivalents of minterms in ascending order with respect to the number of 1 bits, okay, this bits present in it. This is step 2. So what this step means, let us understand. Okay. So here basically what it means is that first we have to arrange them in certain groups depending on the number of 1 bits that are present. So here in 1 there is only one single 1 bit is present. See, in minterm 1 there is only single 1 bit, okay, single 1 bit, this one, this single 1 bit. Then in minterm 3 there are 2 1 bits, double 1 bits, and so does 5, minterm 5, 2 1 bits. Okay, so this will go in one category, in one group. These two will go in the double 1 bit category, okay, double 1 bit category, and then Minterm 7, which consists of 3 1 bits, it will go in another category, which is triple 1 bit, okay, because 3 1 bits are present. So here we'll be forming a table, okay, let's call it table 1, where we have arranged all the minterms in ascending order depending on the number of 1 bits that are present. So first is 1 with expression A bar B bar C and the binary equivalent 0 0 1. Then we have 3 and 5, okay, we have 3 which is 0 1 1 and 5 which is 1 0 1. This is one group, and then we have 7 which is 1 1 1. Okay, so let us put them in boxes, highlight them using boxes so that we understand in which group they belong. This grouping is very important. Okay, this is one group consisting of single 1 bits, this is another group consisting of double 1 bits, and this is another group which consists of only 1, and the top group also consists of 1, which is triple ones. Okay, so let's call it group A1, okay, this is group A2, and this is group A3. See, all the minterms are arranged in ascending order with respect to the number of 1 bits present. Another important thing to take care of here is that we have not arranged the minterms in terms of their magnitude. Okay, these magnitude 1, 3, 5, 7, not that. We have arranged them with respect to the number of 1 bits that are present. So let me use another example to make this point clear. Suppose we have minterms 1, 3 and let's say 4. Their binary equivalents are 0 0 1, this is for 1, 3 it is 0 1 1, 4 will be 1 0 0. So if we have to arrange them in ascending order in terms of their magnitude, it will be first 1, then 3, then 4. But if we have to arrange them in ascending order depending on the number of 1 bits that are present, then if you see here in 1 there is single 1 bit, and in 4 also there is single 1 bit. So what will happen is that 1 and 4, they will come in one group, okay, 0 0 1, 1 0 0, and 3 will come in another group because it has 2 1 bits. So this is one group, this is another group. Even if the magnitude 4 is greater than 3, it will come before 3. 3 will come last in terms of the ascending order arrangement with respect to the number of 1 bits, because the minterm 3, it has 2 1 bits, whereas minterms 1 and 4, they have single 1 bits. Okay, so this is the point that I am trying to make here. So here they have been arranged in ascending order with respect to the number of 1 bits that are present. Then step number 3, okay, step 3 is, again each step try to understand what I am trying to say, okay. Formation of Minterm pairs with respect to the binary equivalents differing by 1 bit position. Okay, please understand what I'm trying to say here. Okay, we have to form Minterm pairs of these binary equivalents which we have, which differ by only 1 bit. Okay, so let us try to understand what it means. Okay, first I will give an example, then I will be forming Minterm pairs. Okay, so let us say we have this and this, these two. Okay, these two binary equivalents we have, this is for 0 and this is for 1. Okay, so if you see, if you compare these two binary equivalents 0 0 0 and 0 0 1, you see that these two binary equivalents, they are same in all respects. Okay, here also it is 0 0, here also it is 0 0, it is same up to these two bit positions. Okay, but here at this bit, the LSB bit, it is differing by 1 bit. Here it is 0, here it is 1. Here at the last bit, they are differing by 1 bit position. At the last bit, it is differing by 1 bit position. Okay, this is called as differing by 1 bit position. Okay, so let us say we have another example. We have 0 0 0 0 1 1. This is for 0, this is for 3. Here if we compare these two bits, then here these two are same. Okay, these two bits are same, the MSB bit, but the middle bit and the LSB bit, they are different here. Here it is 0 0, here it is 1 1. They are differing here in these 2 bit positions. So here it is differing in 2 bits, okay, position. Okay, we want this. We want to identify two minterms, pair of minterms, okay, pair of minterms that differ by only 1 bit position. This will be called as a Minterm pair, which will be used in Quine-McCluskey method, QMT tabular method. This is called as forming a Minterm pair which is differing by 1 bit in only one position. They are different. So what we'll do, if there is differing in only 1 bit position, we will keep the similar bits as it is 0 0, which are same, and the position where it is differing, okay, the position where it is differing, we will replace it with a blank space, a dash, just like this. Okay, so let us do a few more so that we are clear about what I am saying. Let us say we have these two binary equivalents 1 1 0, 1 1 1. Here also they are differing in only 1 bit position. Here it is 0, here it is 1. It is similar in these 2 points, okay, 1 1 1 1. So in QMT method, what we will do, to form a Minterm pair, we will keep the similar bits as it is, and the position where it is differing, we will replace it with a blank space or dash. Similarly, let's say we have 0 1 0, 0 0 0. Here these two binary equivalents, they are same here and here, okay, but it is differing in this position, the middle position, the middle bit position. So here we'll keep the similar bits as it is and we'll replace the bit position where it is differing by 1 bit as a blank space, dash, 0 dash 0. Okay, similarly, let's say we have 0 1 1 1 1 1. Here they are same in these 2 points, okay, here these 2 bit positions, the middle and the LSB. in the MSB position it is changing. Okay, so we'll replace this position where it is differing by a dash or a blank space, and we'll keep the similar bits as it is, identical bits as it is, which is dash 1 1. Okay, we'll be doing like that. Okay, so you're clear about what I'm saying when I say formation of Minterm pairs with respect to binary equivalents which are differing by 1 bit position, only 1 bit position, that is only one position, whether it is the middle bit, the LSB, MSB or anywhere depending on the number of bits there are, it should only be different in one position, not 2 or 3, then it will be different. Okay, so you are clear about it. So let us erase all these. Okay, so now we'll be forming Minterm pairs. So if you see, we have to form Minterm pairs between adjacent groups here. Okay, Minterm pairs will be formed between group A1 and A2, A2 and A3. There can never be a Minterm pair formed between A1 and A3 because there will be difference in 2-bit positions, because we have arranged it in 3 groups depending on the number of ones that are present. So Minterm pairs are only possible between adjacent groups. This is another important thing. Minterm pairs can only be formed between binary equivalents or minterms of adjacent groups. That is, Minterm pairs can be formed between groups A1 and A2 or A2 and A3. It can never be formed between A1 and A3 because they will be differing in bit positions at 2 or more bits. Okay, like that, not 1 bit. So let us see. We'll compare the minterms of group A1 and A2. So let us see 1 and 3. Okay, 1 and 3, let us see. 1 is 0 0 1, and here 3 is 0 1 1. Okay, 0 1 1. So here if you see, it is same here. Okay, it is same here, 0 0. Here it is different, here it is 0, here it is 1, here it is same 1 1. Okay, so here it is differing in this middle bit position, 1 bit, that is differing in 1 bit position. So here a Minterm pair can be formed, which is 1 3, will represent a Minterm pair like this. Okay, this is one Minterm pair and it is represented as, we will keep the identical bits as it is, that is 0 in the MSB, 1 is the 1 in the LSB position, and the middle bit we will replace it with a blank space or dash. Okay, this. Then let us compare 1 and 5. Okay, 0 0 1 1 0 1. Okay, 1 is 0 0 1, 5 is 1 0 1. Okay, so here if you see again, here it is 0, here it is 1. It is differing here in the MSB position. Here it is 0, here it is 0, it is identical. Here it is 1, here it is 1, it is identical. So it is identical in the middle bit and the LSB bit, but is differing only in the MSB bit. So yes, a Minterm pair can be formed. This is 1 5, a Minterm pair, and it will be represented as dash blank space in the MSB where the bits are differing, and then we'll keep the identical bits as it is. So in between groups A1 and A2, 2 Minterm pairs are formed. Okay, between groups A1 and A2, these are the 2 Minterm pairs, 1 3 and 1 5. Okay, then we will compare the the minterms of group A2 and A3, adjacent groups A2 and A3. So here 3 and 7, okay, so let us do 3 is 0, 1, 1, 7 is 1, 1, 1. So it is clear here also these two bits are same, 1, 1, 1, 1, the middle and the LSB bit. Here it is differing, here it is 0, here it is 1. So yes, a minterm pair can be formed here, 3, 7, okay, this is a minterm pair, and the expression of this minterm pair will be a blank space in the position where it is referring, that is the MSB position, and will keep the identical bits, the similar bits as it is, dash 1, 1. Similarly, we will compare minterm 5 and minterm 7, minterm 5 of group A2 and minterm 7 of group A3. 5 is 1, 0, 1, 7 is 1, 1, 1, okay. So here also these two bits are same, MSB, the LSB bits are same, they are differing here in the middle bit, they are differing 1 bit position. So yes, a minterm pair can be formed, 5 and 7, it is a minterm pair, and the expression is, will keep the identical bits as it is, that is 1 in MSB, 1 in LSB, middle bit will be replaced with a blank space or dash, okay. So here these are the minterm pairs between groups A2 and A3, okay, these are the minterm pairs between groups A2 and A3. So next is forming a table of minterm pairs, okay, forming a table of minterm pairs. So it is step number, I think, 4. So here I am explaining in detail, that's why it is taking some time, but once you understand it, I will be going quickly, okay, without wasting any time in the middle. Here I am showing you in detail how the minterm pairs are formed. That's why it's taking some time, but it is not lengthy once you practice a lot of questions related to it. Just by looking at the table, the binary equivalents, you can form minterm pairs in your mind, okay. But for that you have to practice a lot of questions using the conventional lengthy process, okay. Then you will gain that expertise where you can form these pairs in your mind, okay. So step 4 is table of minterm pairs, okay. So minterm pairs and their binary equivalents A, B, C, because 3 bits are there. So first minterm pair that we formed is 1, 3, 1, 5, 3, 7, 5, 7. Okay, let us write them. 1, 3, 1, 5, then is 3, 7, 5, 7. 3, 7, 5, 7. Okay, so the representation of 1, 3 is 0 dash 1, okay, 0 dash 1, 1, 5 is dash 0, 1. Why I am representing it this way, I have already explained. We are keeping the similar bits as it is, and where they are differing by 1 bit, we are replacing it with a blank space. So 1, 5 is dash 0, 1. This is one group, okay, 1, 3 and 1, 5. Why? Because these are the minterm pairs formed between the minterms of group A1 and A2, okay, group A1 and A2, adjacent group, A1 and A2 adjacent group. Let's call it group B1, okay, let's call it group B1. Then we have another 2 minterm pairs, 3, 7, 5, 7. their binary equivalent is dash 1 1 1 dash 1. Okay, dash 1 1 1 dash 1. Okay, so this will be another group, okay, between A2 and A3. These are the Minterm pairs formed between A2 and A3. Group A2 and A3. This is, let's call it group B2. Okay, so next step is we have to compare each minterm with the minterm pairs. Okay, we have to compare each minterm with the minterm pairs. So how we'll do it? Okay, let's use a different page because space is running out. Okay, step, I think it is step 5. Okay, step 5. I think it's step 5. Let's see. Step 4, yes, step 5. Step 5 is comparing each minterm with the minterm pairs that are formed. Okay, so for that we will list all the minterms in one column and all the minterm pairs in another column. Okay, so the minterms are 1, 3, 5, 7, and the minterm pairs that are formed are 1, 3, 1, 5, 3, 7 and 5, 7. These are the minterm pairs that are formed. Now what we want to check here is that are all the minterms that are present, okay, that are given to us in the question, okay, are all the minterms that are given to us in the question, that is 1, 3, 5, 7, are they all involved in pair formations, minterm pairs? Has anyone been left out, is not involved in a pair? That what we want to check. So here minterm 1, it is present in a minterm pair, yes, 1, 3, 1, 5, yes, it is involved. So we will put a check mark here. Similarly minterm 3, it is involved in a minterm pair with 1, 1, 3, yes, 3, 7, yes, so yes, this is also, it is also involved in a pair. 5 will see, yes, 5, 1, 5, yes, 5, 7, it is involved in 2 minterm pairs, okay, so we'll put a check, it is involved. 7, yes, 3, 7, 5, 7, yes, this is also involved. So all the minterms that are given to us, that are present in the question, they are involved in pairs, involved in minterm pairs. Okay, no one has missed out. Okay, no one has missed out. This is comparison of minterm pairs. Then we have to do another step, that is forming pairs of minterm pairs, or it is also called as merging of minterm pairs. Okay, merging of minterm pairs. So again it is based on the same concept of formation of minterm pairs. Okay, it is based on the same concept. Okay, so let us understand what it means. When we are forming minterm pairs, we were seeing that whether two particular minterms, their binary equivalents, they are differing in 1 bit position or not. Okay, that we are interested in. In formation of minterm pairs, merging of minterm pairs, what we are looking for is the binary equivalents of these minterm pairs here. Okay, these minterm pairs, their binary equivalents. So let us copy it here. Just copy this table here, okay, because we'll be using it. Okay, let us keep it here. So what we'll be doing is that we will be looking at these binary equivalents of the minterm pairs that are formed in, considering these blank spaces, then we'll see whether these minterm pairs of adjacent groups, they are differing by 1 bit position or not. Okay, so let us try to understand what I'm trying to say. See, let us say there is one minterm pair. Let's call it minterm pair 1. Okay, minterm pair 1, and it has the binary equivalent dash 0 1. Okay, and there is another minterm pair from adjacent group which has the binary equivalent dash 0 0. These are the two minterm pairs from adjacent groups that we are comparing, and this is their binary equivalent. So here if you see, these two are blank spaces, identical. Blank spaces means identical, they are the same. Here it is 0 0, same, identical, but here it is 1, here it is 0, here it is differing. Okay, it is differing by 1 bit position. In 1 bit it is differing. So yes, these two minterm pairs can be merged. So how they will be merged? We will keep the identical bits as it is, that is, we'll keep the dash as dash, we'll keep the 0 as 0. We will replace this differing bit with another dash, that is dash 0 dash. Okay, let us take another example. Let us take another example. Okay, so we have again another minterm pair. We have minterm pair 1, let's say. It has a binary equivalent given as 1 0 dash. Okay, then we have another minterm pair from adjacent group, and that is given as 0 0 dash. So here if you compare these two minterms, here they are differing, okay, in the MSB bit. Here it is the same 0 0. Here these two are blank spaces, so that is also same, they are blank spaces. So here it is differing in the MSB position, 1 bit position and the MSB. So yes, these two minterm pairs 1 and 2 can be merged, and the merged minterm pair will be represented as, we'll replace the differing bit with a second blank space, we'll keep the identical bit as it is, that is 0, and we'll keep the blank space as it is. So dash 0 dash. This is the binary equivalent. Let us take another example. Here let's say it is dash 0 1, here it is 1 0 dash. So here if you see, here it is not identical, it is different. Here it is a blank space, here it is 1 present, here it is the same, here it is again different, here it is 1, here it is a blank space. So this minterm pairs, okay, pair 1 minterm pair 2, these cannot be merged because they are differing in more than 1 bit position. So this merging cannot be done. This can be done. Okay, so this is what we are going to do. So let us erase all of it. Okay, so how we are going to form the minterm merging of minterm pairs? We will be comparing the minterm pairs from adjacent groups. Group B1 will be compared with group B2. So we'll compare minterm pair 1 3 with 3 7, then 1 3 with 5 7, then 1 5 with 3 7, then 1 5 with 5 7. So let us compare 1 3 and 3 7. Okay, minterm pairs 1 3 and 3 7. 1 3, it has the binary representation 0 dash 1, 0 dash 1. Okay, 0 dash 1, and 3 7, it has the binary representation dash 1 1. Okay, dash 1 1. So here, as you can see, here it is different in the MSB position. Here it is 0, here it is a blank space, so this cannot be formed, this is differing. Here it is a blank space, here it is 1, so this is also differing in this bit. Here it is same 1 1, but they are already differing at 2 positions, so this merging cannot be done. 1 3 3 7 cannot be merged. Okay, it is not possible. So let us take the second condition, or the second case, 1 3 with 5 7. 1 3 and 5 7. So 1 3 is, again 1 3 is 0 dash 1, and 5 7 is 1 dash 1, 1 dash 1. So here if you see, here it is different in the MSB, it is 0, here it is 1, here it is blank space, here it is also blank space, dash dash, so it is identical. Here it is 1, here it is 1, so it is identical. So yes, this merging of 1 3, and here it is 5 7, this is 5 7, this can be done, and the merged minterm pair will be 1 3 5 7. Okay, this is the merged minterm pair, and their binary equivalent is, we will keep the identical bits as it is, that is dash and 1 in the middle and the LSB, and the position where it is differing, here it is 0, it is 1, we'll replace it with another dash. Okay, this. Okay, this 1 3 5 7. So this is a merged minterm pair. Then we have to compare 1 5 with 3 7 and 1 5 with 5 7. So 1 5 3 7. So let us shift it slightly downwards. Okay, so 1 5, it is how much? Dash 0 1, and 5 7 is 1 dash 1. So here if you see, here it is differing, blank space 1, here it is differing 0 and blank space, here it is same, but it is not sufficient to form a merged minterm pair because it is differing at 2 positions. So 1 5 5 7 minterm pairs cannot be merged. So let us see another condition, that is 1 5 and 3 7. Okay, 1 5 and 3 7. So 1 5 is dash 0 1, and 3 7 is dash 1 1. Okay, so here it is identical, blank space, blank space. Here it is 0, here it is 1, so it is differing here in the middle bit position. In the LSB it is same 1, here it is also same, so it is differing in only 1 bit. So yes, this merging can be done. 1 5 3 7 merged minterm pair can be formed, and its binary equivalent will be keeping the identical bits as it is, dash, differing bits will be replaced with another dash blank space, and 1 will be kept as 1. Okay, the tick marks are kept as it is, the cross marks where it is differing we're replacing it with a blank space, just like we did with the formation of Minterm pairs. So there are two merged Minterm pairs that are formed. One is 1357, another one is 1537. So if you pay attention here, these two merged Minterm pairs, they contain the same minterms. Here it is 1357, here it is 1537, just in different order. Here 13 then 57, here it is 15 then 37. But these are repeated because they contain the same minterms. They contain the same minterms, so they will be considered as repeated, and their binary equivalent is also similar. So they will be considered as repeated and will be replaced with a single merged Minterm pair called as 1357 in proper order, and its binary equivalent will be dash dash 1. Okay, for A, B and C, these two. Okay, so here for this whole thing, table of Minterm pairs, there is only one merged Minterm pair, which is 1357. Okay, then let us remove it from here. We have formed the merging of Minterm pairs. Now step 7, we have to compare the Minterm pairs with the merged Minterm pairs. Merged Minterm pairs. Okay, just like we compared the minterms with Minterm pairs, just like we did it here, comparing the minterms with Minterm pairs, here we'll be comparing these Minterm pairs with the merged Minterm pair, that is 1357. So the Minterm pairs will be listed in one column, and here we have only one merged Minterm pair, so we'll be also putting it in another column. So it is 1357, and the Minterm pairs are 1357, oh sorry, 13153757. So here also the purpose is the same. We are checking whether any of the minterms has been missed. Okay, whether any of it is repeated, whether they are involved, whether they are covered in the merged Minterm pair. Okay, so the minterms that are present in the Minterm pair, whether they are also present in the merged Minterm pair, that we want to check. Okay, see 13 is present here. 13 is present in the merged Minterm pair. So okay, this is check. 15 is also present in this merged Minterm pair. So this is also check. 37, okay, 37 is also present in the merged Minterm pair. 57, yes, 57 is also present in the merged Minterm pair. So there is no need to include any of these Minterm pairs in the final expression of the Boolean expression. We only require this merged Minterm pair because it covers all the essential prime implicants. It covers all the essential prime implicants. Okay, let me give an example to make the point clear what I am trying to say. Let us say we have, I am giving a different example here, okay, different from this. Just get out of this question for 1 minute. I am just trying to give you a different example. Let us say we have minterms 1, 3, 4, 6, okay, let's end 7 like this, and we have Minterm pair, merge Minterm pair. This is Minterm pairs 1, let's say 2, 3, 5, 4, 5, 6, 7, like this. We have Minterm pairs. Let us remove this one. Okay, like this we have, and we have merged Minterm pairs like this. 1, 2, 3, 5, and let's say 1, 3, 5, 7. We have these two merged Minterm pairs. So if we compare these Minterm pairs with merged Minterm pairs, see 1, 2 is present in 1, 2, 3, 5, okay, it is check marked. 3, 5 is present here in merged Minterm pair, that is also check marked. 4, 5. 5 is present in both the merged Minterm pairs, but 4 is not present. 4 is not covered in the merged Minterm pair. So we will highlight this. Again, 6, 7. 7 is there in this merged Minterm pair, but 6 is not present any of the merged Minterm pairs. So again we will be highlighting this. So here the essential prime implicants are 4, 5, 6, 7, 1, 2, 3, 5 and 1, 3, 5, 7. These 4 will be considered. Okay, these 4 will be considered. Why? Because here 4 is not covered here. Okay, 4 is not covered here. 6, 7, 6 is not present in any of the merged Minterm pairs. So we have to consider these 4. So like this. That's the reason we are comparing each of the minterms with the Minterm pairs and each of the Minterm pairs with the merged Minterm pairs. So here if you see, all the minterms that are present in the Minterm pairs, they are also present in the merged Minterm pair. 1, 3, 5, 7, they are all present in the merged Minterm pair. So there is no need to repeat any of these. Okay, there is no need to repeat any of these in the final expression. This merged Minterm pair is enough. So now we will look at the binary expression of the merged Minterm pair. 1, 3, 5, 7. Merged Minterm pair, it has the expression dash dash 1. Okay, blank space 1. The bit positions are A, B, C. So here the final expression will be this. The bit which is there, not the blank spaces, this one. And in SOP, the uncomplimented terms or variables, they are represented as 1. So here the final minimized Boolean expression will be, C. This. Okay, for this given Boolean expression, this one, which we had to simplify, FABC is equal to Minterm 1357, the minimized Boolean expression is this, C. Okay, this. So if we want, we can confirm it with the help of K-map simplification. Okay, 3 variable K-map simplification. So let us do that to be clear about it. So we'll be drawing the K-map, 3 variable K-map. If you remember, this is the format. A, B, C, okay, 0 and 1, here it is 0, 0, 0, 1, 1, 1, 1, 0, here it will be A bar, here it will be A, here will be B bar, C bar, B bar, C, B, C, B, C bar, and each of these cells represent a particular min term, which is 0, 1, 3, 2, 4, 5, 7, 6. Always remember 0, 1, 3, 2, not 2, 3. Here also 4, 5, 7, 6, not 6, 7. Okay. Here people make mistakes. Okay. So the expression which is given 1, 3, 5, 7. So 1, 3, 5, 7. So if you see here, we can form a quad. Okay, this is a quad. We have to identify the common, variables in this quad from both the horizontal and vertical, cells. Here there is nothing common. Here it is a bar. Here it is a. Nothing common in the horizontal side. In the vertical side, we have this C common. B bar B, only C is common. So the minimized Boolean expression is C. So we have confirmed it through K-map. Another interesting point, this quad which we have formed here, consisting of 3 min terms 1, 3, 5, 7, it is similar to the merged minterm pair which we have got here. The merged minterm pair. Okay, this one. This merged minterm pair is the same way we got the quad in the K-map. Okay, this. So like we form pairs in K-maps, pairs, quads, octets, in the same way we also form first minterm pairs, then the merged minterm pairs is the formation of quads, and then from that quad we got the final result. So essentially both the K-map and the Quine-McCluskey method, it is the same, but here it includes a different process of achieving the same result. Destination is the same, but the path which we have taken is different. Okay, so the same result. So here the minimized Boolean expression is C through K-map also, and also through the QMT method. Okay, QMT method and K-map method. So here, if you want to solve the given Boolean expression, we did it in almost 1 minute, a few seconds through K-map. So you would ask, why go through this unnecessarily hassle of QMT method? See, the purpose of making this video was to make you understand the different steps that are involved in the QMT table method. QMT table, I will never advise you to solve a 3 variable, 4 variable, even a 5 variable Boolean expression using QMT method. It is never used for that purpose. For when the variables increase greater than 5, 6, 7, 8, then the QMT method comes handy, because it is lengthy of course, but the chances of mistakes will be less, and it is almost impossible to use the K-map to solve 6, 7, 8 variable Boolean expressions. 6, 7, 8 variable Boolean expressions never come in the exam, but in order to have an idea of what the QMT method is, the Quine-McCluskey method, I first started with the 3 variable Boolean expression. Then we'll be solving majority of questions with respect to 4 variable. Then we'll be solving some questions related to 5 and 6. So yes, the first 2 questions, 3 questions, it will be on 3 variable. Then we'll be moving to 4 variable, then 5 variable. So here it took a lot of time because I explained a lot of things step by step. There are a lot of steps here, almost 8 steps. Okay, 8 steps, 7 steps there are. Each steps involved a lot of process, a complicated comparisons, and the possibility of making mistakes, if you are a beginner to this, it is very high, and you will make mistakes, but the more number of problems you solve, the mistakes, it will become less and less, and ultimately you will reach a point where you can form these minterm pairs just in your head, just like looking at the binary equivalents right from the step 1. Okay, from step 1 you can form the minterm pairs in your head. Just from here you can form the minterm pairs in your head, directly write them out in their binary equivalents and directly reach the result, and will take almost 5 to 10 minutes to solve a question. Okay, normally it takes 10 to 15 minutes or 20 minutes, but here as I explained a lot of things to you, highlighted a few things, that's why it took a lot of time. In the next series of videos we'll be cruising through different steps. I will be skipping a lot of steps. Okay, directly I will be forming binary equivalents. So I will request you to watch this video, the introductory video, where I have explained everything in detail. Okay,